So good afternoon. My name is Carnimeo, and I work here at CISA in the Quantum Espresso Development Group. In this presentation, I will speak about the Quantum Espresso project, and especially with special attention on our recent work in tackling the exascale computational performance in the code development and in the HPC framework. I will briefly present at the beginning of the presentation the Quantum Espresso project as a whole, so the overall features, and then I will focus more in the work that we do here in porting the code to HPC exascale architectures, with particular focus on GPU and heterogeneous computing. And finally, I will show very briefly some results, numerical results made on molecules and materials, showing the performance that we get using the code in its various features, the various features available for the code. So Quantum Espresso is an open source suite of codes. It's not just one single code. There is a suite with different executables, different subprograms for the calculation of electronic structure of molecules and materials. For those who are not in the field, to say it in a simple way, it means that basically the code take in input the geometrical parameters of molecules and materials that are under study, that the user wants to study, and it provides in output the molecular properties chosen by the user. So different kind of properties, thermodynamics, electronic structure, spectroscopy. There is a large ensemble of properties that can be computed by the different subprograms of the code. As I was saying, Quantum Espresso is an open source project. And an important thing is that the project is a community project. This means that there is a broad community spread all around the world of users and developers of the Quantum Espresso code. This geographical distribution shown here has been kindly provided by the Quantum Espresso Foundation, that is the entity that helps with the management of the project and the dissemination of the code. So here we get this distribution by analyzing the papers that have been published, citing the main Quantum Espresso papers and taking the affiliation of the authors. So we found that most of the users are from US, Europe, and China and India together. But basically, we have contributions from almost every country in the world. Also from the Quantum Espresso website, we can extract some information about the impact of the code. Nowadays, we have more than 35,000 downloads of the code, 20,000 citations and 50,000 authors. And also here, the geographical distributions of the downloads resembles the geographical distribution I have shown before of the papers. Mostly, the users are from the academia field, but there is also a significant part of users coming from industry and private sector. Of course, it is more difficult to collect data coming from private institutions, because in the public field, there are more data publicly available. Instead, with industries, we have to work a little bit to extract the data of the usage of Quantum Espresso. However, we did it. And we have found that basically there are three main clusters of companies that are using Quantum Espresso. The first one are the mostly software houses that work in the same field as Quantum Espresso, so molecular and material sciences. And they usually embed or integrate or interface Quantum Espresso in their own software stack. It is because, for example, for their business, Quantum Espresso can be a strategic asset because it allows to perform a simulation of materials. For example, here we find Schrödinger, Matera, Material Square. Then there is another cluster of companies on which we know that they work on Quantum Espresso because we work with them. With them, we have a close collaboration with their developers because these are mostly hardware vendors. So they provide the hardware on which HPC machines are based, especially GPUs, and we work together with us because it is, of course, a mutual interest to have Quantum Espresso working efficiently and optimized on different hardware. So with them, we have a close collaboration. I will come back on this later on. And finally, there is a huge bunch of industries for which looking at the article published or their websites or other information, we know that they have used at least once Quantum Espresso for their research work. And you can see that it is quite a large number of companies. Finally, last year, we founded also a company here at CISA. It's called Materis, whose mission is to provide numerical simulations of molecules and materials as cloud services. The basic idea here is to provide workflows or vertical applications where we simplify the usage of Quantum Espresso in order to broaden the community of people using the code, especially in the private sector. This is an initiative that was recognized by CISA and started last year. So, as I was saying, Quantum Espresso is an open source software. The main foundings behind the project are mostly public institutions and projects. Probably the most important founder is CISA, and this is because this is indirect, of course. It's not that CISA gives money to the Quantum Espresso, but inside the Quantum Espresso code, there are a lot of methods and algorithms implemented by the research staff working at CISA. And since the project is going since many years, the contributions from the research staff of CISA is relevant. And instead, moving to direct foundings here, we have the MAX project that for sure is one of the most important founding source for the Quantum Espresso project. MAX means material design at the exascale, which means that the main target of the project is the simulation of molecules and materials using massive computational resources. In this project was confirmed last year for the third time, which means that there were two previous editions that which we applied, we did the work, and then it was confirmed again. And Quantum Espresso here is one of the main codes, is one of the lighthouse codes, which means that most of the developments that are done within the MAX project are done in the Quantum Espresso code together with the other codes that are listed here. In parallel, last year, with the PNR foundings, it was founded the National Center for High Performance Computing, Big Data and Quantum Computing. And this is a large consortium of public and private institutions. And one of the research branches that are done here is called the Spoke 7, devoted to material science. And in this, within the material science field, Quantum Espresso is again one of the flagship codes. And finally, some of the developments that have been done in the last year in the Quantum Espresso code were also founded by the Pro3 joint program. So this was, sorry for probably a lengthy introduction of the project. Now let's move a bit in what we do as developers of the code. So as I was saying, the main trend of the Quantum Espresso development is trying to achieving exascale performance. Of course, this is a community project. So along the year, we also have merge requests from people from all around the world, and everyone who wants to push their own implementation, new features is welcome. But here I'm speaking about the development that we do here, let's say in the core development group of Quantum Espresso. So again, for those who are not in the field, we have to say, let me just explain that for those who are working in the material science field, usually we have a lot of methods with different accuracy, and the more accurate you want to simulate your molecule or your material, the more you need computational power, of course. And also the same applies in the system sides. So the larger the molecule you want to simulate, the more complex is the material you want to simulate, the more atoms you have in your system, and the more you need computational power. So enabling HPC and massively exploitation of computational power, it means that we can give the users of the code and also the researchers working with Quantum Espresso the freedom to choose accurate methods to treat large systems with to solve realistic problems. And this is also confirmed by the fact that using Quantum Espresso, there is a plethora of technological applications that are based on Quantum Espresso simulations, like batteries, spectroscopies, or surface science. Here we try to classify the types of applications that have been done that can be found in literatures. There is a large cluster of works that are based on solid-state physics, like device microelectronics, semiconductors. There is another big cluster of works in the field of green technologies, like catalysis, organic electronics, and there are also many other fields in which these simulations are done, for example, spectroscopy, electrochemistry. The importance of using HPC resources is also confirmed by European Union with the EUR-HPC joint undertaking program. Basically, it finances the countries in Europe to put on production HPC machines. Nowadays, the most powerful machines are in Italy, Leonardo and Cineca. In Finland, there is Lumi, and in Barcelona, in December, it was made on production Mare Nostrum. These are called pre-exascale, which means about half exascale of computational peak performance. And on the next year, it is expected Jupiter in Germany, that will be the first exascale machine in Europe. So at this point, one might argue, why do you need to put that much effort in exploiting computational resources? Once you have your code, why don't you just ask thousands of MPI, highly massive parallelism? Why do you need to put that much effort? There is a lot of reasons behind this. There is the problem of MPI communication bottlenecks. You have to choose the right algorithm, because an algorithm that is efficient running serial or with the low rank, with a few number of ranks, might be not efficient if you use a massive parallelism. But the main reason nowadays is that most of the HPC architecture and HPC machines, the most powerful HPC machines available in HPC centers are now based on accelerators. So there is a CPU core, you have accelerator, is a GPU. And from one side, it means that you can exploit the computational power of GPU, because basically it does the calculations faster, because there are a lot of computational cores inside. So once you offload your workload to a GPU, it goes faster. But you have to pay a price for that. The price is that you have to communicate, because there are two different memories. So you have to spend time and to spend the resources to move data from the CPU, from the RAM, where data are usually stored, to the GPU memory. So you also have to think that usually in this type of programs, you have also a CPU parallelism, which is a standard MPI. So if you don't do things properly, instead of going faster with GPUs, you might result in going much slower, because you are stuck in communication bottlenecks, both for MPI communications and host device communications. So communications here between different CPUs, and communications here between GPU and CPU. So our work is to try to keep the price of using the GPU acceleration low in order to speed up performance and usability of the code. This might be quite a hard task. Here I will try to list the various types of problems that we encounter, trying not to go into too much details. So Quantum Espresso, as I was saying, can exploit several layers of MPI parallelism. This is one of the strong points of Quantum Espresso. So when you model a molecular system, you can exploit translational symmetry, which means that basically you can exploit symmetry to fold your molecule. So you can compute a smaller part of the molecule, but then in order to recover the entire system, you have to sample the K points in the Brillouin zone. To say it in a simpler words, it means that instead of solving a large problem for a large molecule, you can solve many small problems for a reduced portion of the system. This is a very nice algorithm, a very nice feature, because these many small problems can be divided in parallel into MPI groups. So you can solve them in parallel with a low communication between the different groups, because the problems are quite independent, not completely, but quite independent. And then inside each group, at this level of parallelism, you can also distribute the basis functions, because you can use plane waves. So you can slice basically your data, you can slice it and distribute different portions of data among different processors or MPI ranks. And then we have also other layers of parallelism, like band parallelization, which means that you can distribute orbitals and orbitals, and linear algebra parallelization. So we can use Scalapack or ELPA libraries to distribute eigensolver and matrix-matrix multiplications. So when we add the GPU offload, we have to add it inside this complex framework of different parallelization layers. The approach we follow is one rank, one GPU. So on top of this, each rank has its own offload code to pass its workload to an accelerator. Another problem that we encounter when doing this work is that the different vendors provide different GPUs, and each compiler has its own features. So if you want to have your code to be optimized for a given architecture, you have to work on it, and you have to keep into account that your code should work also for the other architectures. This is not trivial, and in fact, the very first version of Quantum Espresso on GPU was based on CUDA Fortran. We had problem because we could not maintain that, because CUDA Fortran intrinsically requires duplication of code, which means that we ended up in two different source code, two different repositories, and it was very difficult to maintain, provide bug fixes and releases. So we merged them, changing the programming paradigm. We used OpenACC that is based on directives, and it allowed us to work with one unique source code for both CPU and GPU. And then it turned out that Lumi was accelerated with AMD cards, and the Cray compiler supported OpenMP5 better than OpenACC, or at least we were suggested to work in this way. So that's why now we are starting work. We have started working also with OpenMP5, and we have to make effort to have one unique source code for 3 different executions on CPU, GPU for NVIDIA, and GPU for OpenMP5 for Intel and AMD. I will make the story short. As we move from one programming model to another, there is some software engineering that needs to be done, because we have to think about how to engineer the code, how to do to think about how to do interfaces and to keep things consistent. In this sense, the modularity of the Quantum Espresso suite was helpful, because the suite is made by quite independent modules that are used by many different subprograms, which means that accelerating one module is beneficial for many different applications. And finally, another very important point is that the core, from a numerical perspective, the core part of Quantum Espresso is fast Fourier transforms, because we work with plane waves. So basically, if you see things in a very low level, the basic operation that is done and the point where performance is made is fast Fourier transforms. Since there are so many different layers of parallelism, it is very difficult to have different tasks with balanced workload, which means that it's unavoidable that some tasks have less workload than others. And we don't want that tasks with a small workload should wait for the other task with a very large workload, which means that the correct way of doing things is asynchronicity. So we have asynchronous fast Fourier transforms that are very efficient. They are implemented for NVIDIA and AMD software stack, and now we are working also to do the same on Intel side. This is because there are slight differences between AMD, NVIDIA, and Intel software stack, so we have to work a little bit on Intel side. Just to give you an idea of what I'm saying, the blue bars is a Quantum Espresso execution with regular fast Fourier transforms, so no asynchronicity implemented, whereas the red and yellow bars is asynchronous, are done with asynchronous fast Fourier transform. So it's a significant speed up when you do things properly. All what I've said so far has been published in a recent work on JCTC, where basically we summarized our work in accelerating the quantum espresso code with a performance discussion and some examples. And now I'm going to show you some numerical examples on real molecules and materials, just to give you an idea of the results of the effect of what we have done so far. So let's start from the first ground state properties. Is usually the first thing. This is a chromium iodide system. It's 1,000 atoms and 7,000 electrons. The system was studied for Magnon's dispersions. So it's I took this from another study. You can see the leftmost bar here is an execution for using a 1,400 CPU cores. You can see the other bars are done the same calculations using GPU, and you can see here is one order of magnitude faster, basically from a the time point of view, using only 96 GPU instead of 1,400. Here we have another example. This is quite challenging for plane waves. Is the band structure of titanium dioxide with hybrid functional. And you can see here, the red bar here is the time with 192 CPU cores. This blue bar here is the same task with just using 8 GPUs. Please note that the time scale here is logarithmic, so this is not half the time of the red one, but this is one order of magnitude faster. Here another example. This is the calculation of the state diagram of ammonia, which means basically that each point here is a long Carparinello simulation of molecular dynamics. So here it's quite an intensive task from a computational perspective. And you can see here the comparison between times. The darker bars are times done using CPU. The lighter bar is with GPU. In the field of molecular dynamics, going faster here means that you can run longer dynamics. So in some cases, going faster means that you can do things or you cannot do things. It's quite crucial. And here we have another example. This is a silicon surface. And the calculation here was to compute vibrational properties of the surface, in particular phonon dispersions. And again, here you can see the comparison between the dark bar with CPU-only execution and the light bars, which is using GPU. Again, here, this is the same system, so a silicon surface. Here you see that we have silicon dimers here that have a pi system. And this pi system can be excited by the kinetic energy of an incident electron, which gives rise to a Hills spectrum here that can be computed with the quantum espresso. And here again, you see comparison for this task between CPU and GPU. On average, we found about a speed up from 5 to 10 when using GPU with respect to CPU, depending on GPU architecture that is used, depending on the property that has to be calculated, and depending on the particular molecular system. Usually, if you have K points, you can exploit translational symmetry and you can go much faster. Finally, the last example here is again chromium iodide. This is the computation of Magnon dispersions. And again, here you have the black bars is a CPU computation, the red ones are the same task done on GPU. I'm sorry if I went quite fast. It's just to give a complete overview of what we can do now. So I am about to finish. Let me just tell you a couple of things in future. We will continue the working, especially with the OpenMP5 language, just because the work for NVIDIA with OpenACC started much earlier than this, and so it is quite finished now. We will continue working on optimization of fast Fourier transforms. And finally, one important thing is that we will develop exascale workflows, which means that we will develop automatic protocols of calculations where many different quantum espresso calculations will be chained together to solve a very complex system on a realistic molecular model. And let me just thank the people working on this project. So there is, let's say, this core group of developers of Quantum Espresso here in Trieste, working at SISSA, CNR, and also University of Udine, where Paolo Giannozzi works. And for all these developments, we work in close collaboration with Cineca. They help us with code optimization, benchmark, and testing, and solving technical issues. And also, we work in close collaboration with external collaborators and vendors. So there are people from NVIDIA and Intel that help us with the most tricky technicalities of working with GPUs and optimizing the code. And also there is the Quantum Espresso Foundation that helps with the general management of the project and the dissemination of the code. And thank you for the attention.
Thank you very much. Congratulations for all this work and this nice overview of the latest, let's say, developments of Quantum Espresso towards the exascale computations and general advancements in software engineering.